We saw the equation of how to calculate capillary filling of a system, and that was a simplified derivation because we knew we had a cylindrical channel. So now let's have a look at a non-cylindrical channel and the more general description. So we have a capillary system with a certain shape. We have a solid, and we have, and then somewhere we have a capillary front that may look like this. And the thing we know is that the contact angle theta here is fixed. So here we have liquid, here we have gas, and here we have solid boundaries. How can we calculate now the equations that describe how this capillary filling goes? Well, we know that the total energy of such, if it's a capillary system, that means that the surface energies will dominate the behavior of the system. So we can look at the total surface energy, UT, and that is the sum of all surface energies. So it is the sum of the wet, this is the wet surface, the solid liquid surface is the wet surface. We have the dry surface is the solid gas surface, and we have the liquid gas surface. So the total energy equals the sum of the wet surface times the area of the wet surface plus surface energy of the dry surface plus times the area of the dry surface plus the surface energy of the liquid gas interface times its area. And now to know what is the pressure drop that we're going to get here, we know that pressure equals an energy density. That's what we talked about before. So if I want to know the energy, I can look at what happens if I go from, there's a certain volume VL here, liquid with a volume VL. So if I move this liquid front, for example, and I move it a slight distance to the right, I'm going to have a change dVL here, or a change in volumetric distance, volumetric change of volume of my system, of my liquid, and then I know that this dV gives rise to a change in the total energy that equals, basically I'm going to create an extra little bit of liquid energy and I'm going to remove a little bit of gas. I'm going to add a little bit of liquid volume, remove a bit of gas volume. So I can say that the energy change equals the energy density in the liquid, which is the pressure in the liquid, times dVL. That is the liquid volume I add, the energy of that, and I remove the energy density of the gas times the volume change. So that's the energy of the gas that I remove. So that is the energy change that I do. And I can see this equals, of course, PL minus PG times dVL. Yeah? I know that the pressure, so the driving pressure then, P liquid minus P gas equals du dt over dVL. Yeah? And so with this formula, I can now calculate what is my pressure difference. And let me write it out. So I know du dt stands here, so that equals gamma solid liquid times d, the change of wet area with volume change, plus the solid gas times the change of the dry area with volume change, plus the change of the liquid gas interface. And now I know three things. I know one, my total solid surface, which is this surface plus this surface, this is at any time constant. And it actually equals the wet surface plus the dry surface. So equals A solid liquid plus E A solid gas. And I know that is a constant. So if this is a constant, then I know the derivative of this one is equal 0. So I know that if this equals 0, that I know that any change in the wet surface is the same as a change in the dry surface. So basically what I'm saying, like, if my liquid front moves, I create more wet surface, but I diminish the same amount of dry surface. And I just write that dA solid gas equals minus dA solid liquid. The second thing I know is that the Young-Laplace equation tells me that there's a relation between the surface energy of the solid gas system. Remember, so this dry surface tries to minimize and the wet surface tries to minimize. So solid liquid plus the cosinus theta plus cosinus theta of the gamma liquid gas. There was a Young-Laplace equation where we had a drop. You remember where the droplet tries to minimize itself to get a minimum area. So I know that this is valid at any time. And now I can insert these equations in this one here. And basically what I'm going to do is I'm going to replace the solid gas. So I'm going to replace the solid gas here. And this one here. Let me insert this formula in here. And then I'll be able to write that this formula equals gamma solid liquid so this doesn't change, plus, and now I have this term gamma solid liquid plus cosinus theta gamma liquid gas. So that's this one here times minus d solid liquid dVl. And then I have, of course, my last term that remains unchanged. Gamma liquid gas times dA liquid gas dVl. And now we see that this term and this term will cancel out each other. So I can write equals gamma liquid gas times dA liquid gas dVl minus cosinus theta times liquid gas, gamma liquid gas times dA solid liquid dVl. Or I can even bring this term on forehand before equals gamma liquid gas times dA liquid gas dVl minus cosinus theta dA solid liquid dVl. And this is the fundamental formula here that tells me, so this equals P liquid minus P gas. So for any geometry in a capillary system, I know that my driving pressure will be governed by this equation here. And now we can simplify that. So for a cylinder, in the case of a cylinder, for example, cylindrical channel that we already saw. So for a cylinder, I can simplify that, and I let you do that. But the things that I know for a cylinder is that the dVl, so if this here is a constant cylindrical surface instead of a freeform, it's a cylindrical channel. I know that my dVl I can write times as the cross section of the cylinder times dx. I can replace like that, and the cross section is of course PR square. I also know that in the cylindrical channel, if my liquid front moves, the liquid gas front is at any moment exactly the same spherical surface. So the liquid gas front does not change and its area does not change, and therefore I know that dA liquid gas must be 0. So this term here will fall away already. And the third thing that I can see is that the change in solid liquid surface equals, if I take this into account, equals dx times, because in every movement with a distance dx, I will wet an area that equals dx times 2pr. So if I now insert these formulas in here, I will find exactly, I should find exactly the same formula that we derived before already. The simplified formula.